now we are moving to the next talk, and it's early morning in Europe. So it's my great pleasure to introduce a good friend, Professor Martin Winter. Professor Martin Winter is very well known in the battery field. He is the scientific leader for the Münster Electrochemical Energy Technology, short form MEET. So today it's our great pleasure to have Dr. Martin sharing with us on the topic of processing of components for advanced lithium-ion and lithium-metal batteries. Martin, the floor is yours.
Yeah. Good morning, or I should say late good night to Shirley. Good morning to Europe. Good afternoon to Korea and Asia. It's a great pleasure to be here, and I like to thank the organizers from LG as well as Shirley for inviting me to give a presentation, a very early morning presentation at this LGES Innovation Forum 2021. At the beginning, I would like to introduce you to our sponsors. I just have to mention that we are sponsored continuously by the federal ministries of education and research and economy, by the state ministries of NRW, especially education and science, and also economy, European Union, and also their support from the three institutions, Fraunhofer, University of Münster, and Helmholtz. In Münster, we have, four battery activities, in addition to many groups that are working individually on this. One is MEET. MEET is a university institution that has been established in 2009. Then 5 years later, the Helmholtz Institute Münster, which is part of Forschungszentrum Jülich, has been established. Then in 2019, again 5 years later, the research fab battery cell has been awarded to Münster and is set up at the moment by Fraunhofer with the support of the local scientists. And finally, we have a startup here in Münster working on liquid electrolyte solutions, E-Light. This presentation is actually a joint presentation of Helmholtz Institute Münster and of MEET. As Shirley already said, the title of this talk is quite generic. It's processing of components and materials for advanced lithium-ion and lithium-metal batteries. It is an invited talk, so also the topic is invited by LG Energy Solution. And I have just mentioned here the people who have provided slides for this talk. I should have mentioned many more scientists, because this will be kind of overview talk about activities here in Münster, but this would have then led to several slides because of the number of scientists that are involved here in this presentation. As a starting point, okay, many of us are materials researchers, and materials play their role in the battery cell. So the battery cell is our system, and we need a systemic approach for getting the information about the materials inside a composite electrode or a formulated electrolyte that is then coming finally into the battery cell. And a lot of good active materials have been investigated, and some of them, unfortunately, by inappropriate measures, using inappropriate inactive components, bad processing of the electrode or electrolyte. And this finally leads, though the material is actually good, to bad performance. I believe that especially at the beginning of lithium metal and lithium ion battery research, a lot of good materials have been discarded because we were not able to make proper electrodes and electrolytes out of them. Then you have a bad active material, and whatever you do in the processing or with inactive components, you never get good performance. So also bad performance is coming out. So the goal is to have a good active material, use a proper processing, appropriate inactive components to get the excellent performance. And this is always a compromise, because the material selection and the processing needs to be adapted. So usually a certain material also needs a specific processing. There is, let's say, no general processing on individual materials. We are learning this painfully at the moment with solid state batteries and also lithium metal batteries. Just one example here for processing effects, a very, let's say, timely example. A lot of people are looking now at the so-called rollover failure. This is a new term in battery history. This was called for 30 years and more so-called sudden death phenomenon, but somehow everybody is using now the word rollover now. What is meant basically is that when you are using layered material, NMC, for example, 523, at higher voltages, higher charge voltages, you get out more capacity, but also you have more capacity fade. And then finally, suddenly at about, let's say, 50 cycles or so, you have a rapid capacity fade, which is then called rollover failure at around 50 cycles. This rollover failure has been investigated and observed by many scientists, but what is the reason for it? If we look at just a simple visual inspection of coin cells made from graphite NMC cells, and we see at 4.3 volt and 4.5 volt, we see that we have depositions on the anode in both cases, but the depositions at 4.5 volt are much more than at 4.3 volt. And we have investigated this in several, let's say, papers, some of them quite prominently placed in journals, which are mentioned on this slide. And if we are looking at this with a laser ablation inductively coupled plasma mass spectrometry, which allows us to look at various elements that can be deposited on the surface of a graphite anode, lithium, nickel, cobalt, and manganese, we see that at 4.3 volt, we have a low accumulation of lithium and manganese, and no cobalt or nickel deposits could be really found in the pictures, very little nickel maybe. But at 4.5 volt, we see that all of these elements are present on the surface: lithium, nickel, cobalt, and manganese, and which actually tells us that something has happened at 4.5 volt. What we have found out is that nickel, cobalt, and manganese deposition takes place because of transition metal dissolution, migration and diffusion to the anode, and then deposition at the anode. And these are then the hotspots for lithium metal deposition because the SEI has altered, and then lithium ions cannot go into the material, in the graphite material cannot integrate into graphite as before. And this is very much influenced by electrode processing. Here we see a calendared and a non-calendared electrode. Calendared electrode shows us a rollover failure, a sudden death phenomenon. After about 60 cycles, it starts. The non-calendared electrode cycles very well. And basically, the calendared electrodes, we have locally concentrated spots, island-like spots of transition metals and lithium metal, whereas for the non-calendared, we have a more homogeneous distribution of the transition metals and lithium metal. So obviously, we get improved cycling stability by higher anode porosity and surface area, which of course is not what we want, because electrode processing, especially calendering, should give us highly dense electrode, because this gives us then higher energy density. So there is here a trade-off between what we want from the electrode side and what the materials are delivering. And so we have to make a compromise. This is just an example of how processing is affecting materials performance. Actually, processing and materials are inevitably always connected to each other. And this I want to show with 5 different examples, 3 examples on high-energy lithium-ion batteries, and 2 examples on high-energy lithium-metal batteries. And we will go through these 5 examples one by one. First, the silicon-based anodes and pre-lithiation approaches. So maybe you are not aware of it, but lithium-ion cells really are high-energy cells because of their high voltage. So typically, lithium-ion cell, 1850 cell, has, let's say, for a very high power battery, maybe 1800 milliampere hour, for a high energy cell, more than 3500 milliampere hour at a cell voltage, depending on the cathode, of 3.3 to 3.9 volt. And this gives us specific energies presently of low, high power 120, or high energy 270 watt hour per kilogram for an 18650 cell with a certain volume. If we take a nickel metal hydride cell, a AA cell, that's a different format. This is actually, when we translate it into the same terminology, a 14500 cell with about half the volume of an 18650 cell. This gives us a certain capacity and a certain voltage, 1.2 volt cell voltage. If we normalize this capacity to the volume of an 18650 cell, so we take the same 16.5 cubic centimeter volume, this would correspond to a very high capacity of these nickel metal hydride cells. So nickel metal hydride cells have really much higher capacities than lithium-ion batteries, but the specific energies are less than 100 watt hour per kilogram typically. So what we can take from this slide is lithium-ion batteries are high energy systems because of high cell voltage. And it also tells us why we are so urgently looking at higher capacity anode and cathode material, because capacity, that is really the bottleneck, not voltage. at the moment of the present lithium system. And this leads us to on the anode side to two electrode materials which are in the focus of mostly everybody in our field now: the silicon anode for the lithium-ion configuration and the lithium anode for the lithium-metal battery configuration. And if we see and compare it to the graphite-based lithium-ion batteries, we see that silicon is giving us higher specific energy, and lithium metal, again, even more higher specific energy. This slide does not tell you anything about safety and cycle life. It only tells you something about specific energy. And you get this because in a given volume, you can then use the space for anode and cathode more properly if you use a thin lithium metal anode or even a thinner silicon carbon anode, indicating to you that lithium metal is not a high energy density, but a high specific energy material compared to silicon. And also you can simply increase also then in a given volume the cathode thickness if you are able to create such a cathode which is quite relatively large thickness of more than 165 microns and a lithium metal anode. So at the end you get energy gains with lithium of 60%, up to 60%, and silicon even on silicon 35%. And this is something which is basically related to capacity. A little bit on the lithium side also to voltage, but mainly to capacity. So higher capacity gives us higher energy. This is the motivation for these materials. What we also know is that these materials here, for example, the lithium storage metal like silicon, are having a different SEI formation, but also SEI cycling behavior. Unlike graphite, where the SEI basically forms in the first cycle, lithium storage metals show very large volume changes, have a dynamic material surface. This gives a dynamic interface to the electrolyte, and we have continuous SEI formation, so-called SEI repair. And this leads to continuous electrolyte losses and also continuous lithium losses. And in lithium-ion configuration with limited lithium ions available, this is basically the death programmed inside in a lithium-ion battery. So lithium consumption leads to capacity fade, and capacity fade leads to limited cycle life. These pictures have been created around 2000 and are frequently used by others in newer versions of this picture. So if we are looking at the lithium losses, a lot of people believe that the lithium loss is equal to the charge that is lost in the cycle, especially during the first cycle, but also in the later cycles of lithium-ion battery cycling. And we have indeed a lot of parasitic reactions which are occurring particularly during charge, which can consume active lithium. For example, we have SEI components which are consuming active lithium from the cathode. We have also active material loss on anode and cathode side. We might have some irreversible lithium plating. We just talked about the sudden death rollover phenomenon, which leads to this. And also we have the trapping of lithium, because some of the materials that we are using in anode or cathode do not release all the lithium that is inserted. These are all parasitic reactions which can consume active lithium. But also we have parasitic reactions which do not consume active lithium. For example, redox shuttles, hydrogen formation. We have also metal dissolution deposition, and also many additives, many electrolyte components that we are using do not consume lithium by forming SEI components. They only form a polymer without any lithium. That means electrons are consumed, but no lithium is consumed. So how can we differentiate between the electrons which come with lithium consumption and the electrons which are just consumed without any lithium loss? Because this finally tells us something about our lithium loss, and also is very important to tailor our pre-lithiation process of the cell, which is a processing step. So what we did is we actually developed a method for this. We call this the IRLC method, which is a determination of the active lithium loss, ALL, all by the initial and the remaining active lithium content, by the differentiation of the two. And what we are doing is we're doing a two-step process in a 3-electrode cell with a working electrode, which is, for example, graphite or a silicon-based material. Then we have a counter electrode, which is a cathode material, which should be mostly unaffected by any reaction with the electrolyte. We took here LFP because of the favorable potential. There is not much electrolyte oxidation at LFP, probably nothing. And also we have a lithium-metal reference electrode. In the first step, we are cycling the capacity of the cell between the anode and the cathode. And then in the second step, we are disconnecting the cell, and we are connecting then the cathode LFP with the lithium reference electrode. And then we are inserting again all the lithium that has been consumed from the LFP during previous cycling with the help of the lithium metal anode. And then we know exactly how much lithium has been lost because we are knowing then the capacity from this experiment. And this gives us very interesting results. If we look here at the active lithium loss of graphite against silicon graphite, determined by the IRLC method, we see here two graphs. One where we look at the specific lithium loss in millimole per gram. This is always interesting because we are looking at our capacities in ampere hour per gram, for example, or also our energies in watt hour per gram. But what is more meaningful in a full cell is the specific lithium loss in millimole per ampere hour. So the lithium loss normalized to the capacity, because at the end, in this full cell, you're not balancing the capacities by a kilogram of material, you're balancing the capacities by ampere hour of material. And if we look at the specific lithium loss in millimole per ampere hour, we see here that in the first two cycles, cycle number 1 and cycle number 2, the lithium loss on graphite per ampere hour is even larger than that of silicon. What a surprise. But only after cycle number 3 and then the following cycles, then because of continuous SEI formation, continuous lithium loss, the accumulated lithium losses are higher on the silicon material than on the graphite material. So this method actually tells us something which we counterintuitively, I think, would have assumed different. And with this method now we can go into the pre-lithiation as a process. Pre-lithiation is a process that should be incorporated in the segment-wise step of cell assembly and cell making. So we have electrode manufacturing, cell assembly, and formation and aging. You can apply, depending on the pre-lithiation method, you can apply pre-lithiation during the electrode manufacturing, but also during formation and aging, especially during formation process. And the pre-lithiation route, because we have different pre-lithiation processes, there are, let's say, half a dozen at least, this impacts the electrode manufacturing and cell assembly. We investigated this by comparing two pre-lithiation methods, 2 out of many. We have also done others, but I want to show here just the 2 here. One is the well-known electrochemical pre-lithiation, where you control the pre-lithiation degree by potential. Here, for example, pre-lithiation to 0.5 down to 0.3 volt against the lithium metal counter electrode, or the pre-lithiation degree controlled by the mass of the lithium that has been inserted in the electrode mix. Here we take lithium powder because that is much easier to dose than lithium metal foil. The pre-lithiation by electrochemistry needs a higher experimental effort, but higher reproducibility is also given because basically if you are accurate, no lithium metal remains. The pre-lithiation with passivated lithium powder depends on how precisely can you dose the powder. It has a lower reproducibility and also some lithium metal remains depending on how much lithium metal you are using. Still, I want to mention here, this paper actually has been awarded as a paper in batteries. That's a journal. But I want to mention here that much is technically possible, but at the end you have to think about a pre-lithiation method which is somehow incorporation in the process that you are having in your cell manufacturing, because only then you can find a market where the price is right. So here we see the pre-lithiation project, the impact on first cycle of silicon-based cells on the left-hand side. The red above is showing typical cell behavior without pre-lithiation, where you have a lot of active lithium loss. When you are doing pre-lithiation, then you can compensate for the active lithium loss, and then you have a lithium reservoir of about 10 to 20%, which is very nice, which provides a combined benefit of preserved energy density and increased cycle life. Again, this pre-lithiation must be performed with high accuracy, because otherwise you have remaining lithium metal in the cell, and everybody of us wants to avoid lithium plating. So for pre-lithiation, we should really try to avoid excess of lithium metal after the pre-lithiation process. On the right-hand side, we see an NMC silicon carbon cell, discharge capacity and coulombic efficiency, and we see pre-lithiation gives us a higher first cycle coulombic efficiency, and also the cell capacity increased by 15 to 20% compared to the pristine material. All pre-lithiation methods give us some, let's say, advantage both in efficiency and discharge capacity. I just want to mention here also that depending on the pre-lithiation methods, you are doing it for 10 minutes, 50 minutes, or even 5 hours. So the question is, how long does it really take to pre-lithiate? And there are several methods in the literature that have been used here. Optical detection of lithium metal dissolution, typically you find out it takes more than 24 hours if you do not apply any force, just physical contact. Then you have the endpoint determination via indirect methods. You look at the constant voltage. When does the cell have a constant voltage? It's maybe not so accurate because the lithium and the silicon graphite potential is not very different. And then you also have a constant impedance. They all tell us different hour numbers. So it really depends on, I think, not only on the method, but also how the lithium has been pressed and how the electrode has been processed and so on. Our approach is time-dependent in situ NMR. So we are looking at the lithium dissolution over time, and we are looking at the formation of lithiated carbon over time. Here, 1200 minutes, and this is actually an NMR probe that has been built. So it's a kind of in situ, but in situ to time process. And we then took different amounts of lithium metal. We took 25% of lithium metal. Here we have a complete dissolution of lithium metal. As you see, after about 5 hours, no lithium metal is left, as you see from the intensity of the NMR spectrum, taken from the NMR spectrum. We take 43% of lithium metal as pre-lithiation agent. Not all lithium metal is dissolved, some remains, because then we also see that there is a steady process also maybe after 5 or 6 hours, but some lithium metal is remaining because we see some intensity. And if we take exactly the capacity of the electrode, 100% lithium metal, then we see that some lithium metal remains. So you cannot compensate, obviously, for all the capacity that is needed to lithiate the cathode. So there's always some lithium metal remaining if you take 100% of the capacity of the anode. So this is something which has to be regarded. What we learn here is after about 5 hours, physical lithiation is finished. So 5 hours is quite some time. This was the pre-lithiation topic. Now we are moving fast to electrode processing. Electrode processing is actually something which is very well established. It started with non-aqueous electrode processing. What is coming now into play, because we want to make our cell production greener, and this also regards green materials, but also green processes, is processing with water, deionized water. And this goes in auto-ionization reaction, yielding then protonium, hydronium, and hydroxide ions. And as protons are removed from the solution, more water molecules dissociate, which reinforces the exchange that is shown here. We have an equilibrium between the lithiated NCM and the protonated NCM. This is an equilibrium which can be influenced as any equilibrium by the constituents, for example, by the lithium-ion concentration in the paste, the electrode paste, but also by the proton concentration, that meaning by the pH. Because protons are consumed from the aqueous electrode paste, the pH of the electrode paste increases. Then we have transition metal dissolution, and all this actually instability increases with the nickel content in NCM because nickel is more basic than the other transition metals. So we get a pH increase in the solution, and we also get a lithium poor protonated particle surface by aqueous processing. How does the pH value influence this? First of all, the current collector, which is made of aluminum, which is cheap and can be easily made to thin film foils, is reacting with current collector corrosion. This leads to lower energy densities and higher costs. We also have acid buffer solutions that are possible to mitigate this. Then we have lithium proton exchange is increasing, transition metal dissolution is also increasing. And there's another thing that also the active materials are protected by a coating, which leads inevitably to cost increase and usually also to impedance increase. So not all of these methods are as good as the other, and all of them have some disadvantages. So there is a need to look at methods which are able to make aqueous processing as good as NMP-based processing. One idea is, for example, that you increase the pH value by the addition of LiOH. So then you have to adjust the pH value of the binder solution. This actually means that we have more lithium ions in the cell. That means we have less proton insertion inside the active material. As you see here, when you look at an NMP-based material and a material at higher pH, we get a very similar specific discharge capacity, but not the same. NMP is still a little bit better, but it's much better than the reaction that is taking place at a pH of 7.6. It means almost neutral pH. What is very nice is with aqueous processing, it's much easier to make thick electrodes. Thick electrodes with a loading of 50 milligram per square centimeter we have done in work that has been published recently. This is an electrode which has a thickness of about 250 to 300 micron. The key here is to have a low viscosity binder. Aqueous systems offer a wide variety of adjustable parameters here for these low viscosity binders. And then if you use carbon microfibers to help to integrate to lead to better electrode integrity, but also is optimizing the electrode pore structure of this very thick cathode coating, then you get much better cycling behavior than without CMF. And we see that here with aqueous processing and CMF microfibers, we get appreciable specific discharge capacities. But as you see also, there is a kind of voltage delay at the beginning, so electrode porosity is created. But this is certainly a step forward to thick electrodes. What are the novel approaches that we can do? One is that we are looking at processing additives apart from LiOH. An example is LiTFSI. It's a fluorine-containing salt. It's certainly not the green solution, but it gives you an idea here. If we are using LiTFSI, we get almost a similar performance as the NMP processed electrode. So the lithium-ion concentration really helps. And certainly we have to replace LiTFSI by a greener salt, but I think the principle is shown here very nicely. And also the application of tailored surfactants in the paste is, let's say, a very nice possibility that is especially working very well in aqueous solution, because there are many surfactants that work very well in aqueous solution, not in non-aqueous solution. Due to the polarity of the materials in aqueous processing, which is much higher in aqueous processing, the surface charges can be used to tune the interaction of the solid components. So introduced surfactants can decrease the surface charge differences of the active materials, the conductive agent and the binder. And this leads to more homogeneous distribution of the three, and this leads to better, more homogeneous electrodes. So this is just an example of how aqueous processing is, let's say, continuously improving, also on the cathode side, not only on the anode side. Now we are coming to liquid electrolyte formulation. I want to mention here that maybe in contrast to what many people believe, also the liquid electrolyte is a processed system. So there's a lot of know-how in making a liquid electrolyte formulation. It consists out of several components, at least three. So we have a salt, we have two solvents. One is for high viscosity, one is for low viscosity, one is for good salt dissolution. And usually also we have a couple of additives inside the system. That the electrolyte is probably the most important, maybe not the most expensive component in the battery cell. I think that everybody of us has recently discovered as we look at solid electrolyte batteries. But it's decisive for lifetime power and safety, that's for sure. And also has a direct influence on cost, which is not so high, because actually electrolyte production, liquid electrolyte production is very, very inexpensive, and also the components have become very inexpensive. But it has a very strong indirect influence on the cost, because the operation cost, how long does a cell last, how long does it cycle, how safe it is, that is very much depending on the electrolyte. We have many electrolyte classes. Several of them have been presented at this symposium. I've just seen also solid electrolyte and liquid electrolytes in the previous talks. And we have mixtures of the two. The complexity of electrolytes is given. Usually electrolyte is a multi-component system, at least three, but typically 4, 5, 6 components in the cell, depending on the number of additives and the number of co-solvents to ethylene carbonate. And also the complexity at the interfaces, I do not have to mention this here. The SEI and also the CEI, the interfaces at anode and cathode, have not been fully understood even today. And finally, what I want to mention is toxicity, which is, let's say, something which is not very often regarded, but toxicity is an important element of battery safety. It has to be not disregarded. Battery safety is not only, making a cell hot and see when it explodes. Really, you have to find out what is happening in the cell, what is happening when the cell opens and what comes out of the cell. Reactions of the salt LiPF6 with organic electrolyte solvents usually result in organofluorophosphates, OFPs, which are much more toxic, okay? Several orders of magnitude more toxic than HF. OFPs have similar structures as known chemical warfare. Here, for example, I have shown the structure of the chemical warfare sarin, which is well known. And also here we see on the right-hand side, we see the reaction product of LiPF6 with DMC and DEC. Dimethylfluorophosphate and diethylfluorophosphate have very similar structure to sarin and also very similar toxicity. So basically everybody of us who is using a lithium-ion battery during cycle life is confronted in chemical warfare in his equipment or device he is using. What we are doing with electrolytes in Münster, for example, is we are formulating electrolytes with a high throughput screening system, a fully automated system with a complex user-friendly configuration where robots are basically doing the job for us. So it's an automated, by robots handled, high throughput screening system. System number one is basically a system which allows us to formulate 96 electrolytes by a robot. And system number two allows us to make 96 coin cells, 2 electrode cells, or also 3 electrode cells in cell configuration also made by a robot. So it means every day we can make and investigate 96 different electrolyte systems. And then, because of the data which we have, which is so much, then we have to interpret this data. And also for data interpretation, we have to go into automation. So what we are doing is, together with our colleagues here in Münster working in theory, we are looking for the number of experiments is very high. We are looking for how can we analyze these experiments. And processing and also collecting of data is something which is done by a laboratory information management system. And then the analysis of the data is done with the help of mathematical models. Some of them using artificial intelligence. It means we are feeding them again and again with experimental data that the model does develop and improve. For the conductivity measurements, we have developed in-house cells. We are doing electrochemical impedance spectroscopy just to show here a 96-cell rack for simultaneous impedance measurements that are then done inside a climate chamber. And then we get the data, and the data is shown like here. So we are basically with electrochemical impedance spectroscopy explore the formulation space. In this case, we have a quaternary system. That means we have electrolyte salt LiPF6, we have 2 solvents, EC and EMC, and also we have VC, vinylene carbonate, as an additive. If we have 4 components in the system and we use only 5 different concentrations here between the different components, then already we have 625 measurements, 625, only for 5 different concentrations. So if we want to make more concentrations or more components, we are coming easily in the several thousands of data range. All metrics, as is shown here, are molar because, as I said, molar is more meaningful than, for example, weight percent. In initial study, we are looking here at conductivities between -20 degrees C and +60 degrees C. And here we can see that we are finding in this chemical space that has been shown here, we are finding different domains with high and low conductivity depending on the temperature, as well as where also there are domains where we do not get a stable solution anymore. We get crystal formation, and also we get some anomalous conductivity, which I want to address later. Just to mention here, the fact that we get different conductivity maxima for different temperatures underlines that the dependence of the conductivity on the electrolyte composition is not as trivial as one might think. And there's great potential for knowledge gain if the right tools are used in this data analysis. So here the data analysis is done with the help of mathematical models. This is a polynomic fit, and the polynomic fit uses then coefficients, and these coefficients are called sigma, and there are several of them because the polynomic is consisting of several, let's say, elements. One is actually sigma 0 here. Sigma 0, which is done for a conductivity measurement where we did start at 0 degrees C, the conductivity measurement, and then made a temperature ramp up to higher temperatures. And we use 2 different fits here, linear regression and Gaussian process regression, and both of them give us, let's say, quite good data and actually quite high accuracy. If you look at the number of data which is on the line, this is not bad. The picture left below actually shows us then polynomial coefficient sigma 2, which is also then somehow reflecting parameters of the electrolyte solution. In this experiment, it is conductivity, and we see that we have here an outlier on the bottom right. This outlier is, let's say, very, very strong, because basically we show here a correlation plot. We show predicted data against measured data. And we see at the measured data, this outlier is positive sigma, but the predicted data tells us it's a very negative sigma. So we have here obviously a problem with the data set. So what we did is we had to refine the experiment. So what we did is we did 2 temperature ramps. We went from low to high temperatures, where we see then a weak crystallization, which keeps on until very high temperature, so the crystallization stays. But when we go from high to low temperature, we get a supersaturated system. Crystallization only at the lowest temperature. That is when we started at -20 degrees C. So we changed then the start of the experiment. So we start at 0 degrees C, and please observe then that this experimental data is then completely different if we start at a different starting point. At -20 degrees C, the curve has a different conductivity at when we start at 0 degrees C. In this case, we get the refined data. We are moving up to 60 degrees C, and then we are moving down to -20 degrees C again. And then we get the refined data, which we then put into the mathematical system again, and we see that refined data is much better in comparison to what the predicted data is. So the measured and predicted data is very similar. So this actually tells us very nicely that with the help of artificial intelligence and data processing and refining data both on the theory and on the experimental side, we find something which we have never found when we have used, let's say, typical conductivity measurements. So I think this really shows the power of this method. And it's possible because of the high throughput screening and because of let's say, the use of an artificial intelligence model that is continuously trained and improves over time with the experimental data that is coming. So I think a very nice experiment showing you that maybe many of the conductivity measurements that have been done so far should be, let's say, readdressed, revisited again. Now we're coming to high energy lithium metal batteries very fast. Lithium metal battery, the extrusion process in the 3-step process of lithium metal production is very time consuming and it produces scrap, because lithium metal in foil form is a polycrystalline material. That means if you want to make it very thin, it tends to break and then you produce scrap. So if you want to reduce the amount of lithium in the cell, you have to produce ultra thin foils with less than 50 microns. This makes sense because then the capacity balance in the cell is there, and even in the discharge state, you have the no lithium excess. The lithium metal is then finally in the capacity balanced form. Unfortunately, the price of lithium metal foil increases by this processing with reduction of foil thickness. Also, gas phase deposition is not very helpful because when you want to go to 20 to 30 microns, it takes a long time and is very expensive. And then also what is important is that when you are just looking at how to process lithium metal to thin foils, maybe it's also advantageous to look at the surface composition of these lithium foils because it's important for application. Because the surface composition plays a major importance because, as we know this, because it influences SEI and deposition morphology and so on. So what we are doing is we have our own lithium metal lab that we are setting up at the moment. We are doing here the processing of, let's say, regular lithium foil to a thin lithium foil, and we can get at the moment, let's say, 50 to 30 micron foil thin lithium without any scratches and without any breaks and without any scrap. And also what we are doing here, we are not only diluting the thickness of the foil, we are also diluting the chemistry on top of the foil. And this by a roll-to-roll process. So it's an automatic process, which of course is necessary if you want to make lithium metal batteries finally work in full cell production. So what are we doing? We are doing, first of all, making lithium metal thin, and also the native film, which is inevitably on lithium metal. When you buy lithium metal on a foil, you always have a native film. We also dilute the native film because when we are thinning the lithium, we make more area, and with this also we dilute the native film. What is very interesting, I think, to note is the S-received lithium is always very rough. So you should not wonder that you get dendrite deposition on the S-received lithium because there are a lot of inhomogeneities which lead to preferable sites for lithium metal deposition, and this leads then to inhomogeneous lithium deposition. After roll pressing, you get a much more smooth surface, and also you get a different composition of the surface film. And all this leads to differences in lithium stability. This is really a very, let's say, very bad electrolyte, liquid electrolyte, lithium cells, symmetric cells, and we see after roll pressing, we see some improvement in the consistency of the overvoltages. What you can do is, if you use mechanical lithium metal modification, there are many things which I cannot show today. One is that you are combining it with a chemical process, so that you are making it to a mechanochemical lithium metal modification. For example, you put an iron liquid, and there are plenty of iron liquid that you can use on top of the lithium metal before you roll press it. Then you make the lithium metal thinner, but also you create an artificial SEI by reaction of the iron liquid with the lithium metal. And the mechanochemical modification is really showing a big improvement. This is a green curve showing here, and it's much better than all other experiments where we have no modification, mechanical modification, or separate mechanical and chemical modification. Only when we do it in once, that we do the mechanic and the chemical modification in once during one process, we get the best result. And this also at 10 milliamps per square centimeter, so at relatively high current densities for lithium metal anodes. And finally, I want to come to some very, let's say, simple stuff, because I think the simple stuff is always sometimes the most interesting one. I want to talk about solid-state battery component processing, some basics. And I want to in particular talk about bipolar batteries, because that's a big promise of solid-state batteries compared to liquid electrolyte batteries, that bipolar cell stacks are much easier to make with solid-state batteries than with liquid electrolyte batteries. In fact, many of us claim, because of, let's say, the simpler system, battery system configuration that is provided by solid-state batteries, the energy densities are high, not because of the cell, not because of the energy density on cell level, where we are using a very heavy and also probably a little bit thicker solid electrolyte, but on the stack level, a lot of people are promising high energy density. So let's look at stack level. So as you all know, lithium dendrites are not good, and we need colleagues like my good friend Johannes Kasnachiev, shown here, who is able to suppress lithium dendrite formation by the help of solid electrolytes. That is the promise of solid electrolyte dendrite suppression, or even dendrites are completely eliminated. So then we use the lithium cell with a sulfide electrolyte and also with PEO. So it's a multi-layer electrolyte, and it gives us in a single cell, let's say, normal charge-discharge behavior, not very great, but it shows us reversibility. No short circuits are happening in a single cell. And then we make a bipolar tri-layer cell, a tri-cell stack here, cell 1, cell 2, cell 3. And we are using this, and the advantages of bipolar compared to monopolar stacking are mentioned here again. But charge is not possible. Charge reaction does not happen. And actually, when we look at the open circuit voltage over time, actually this stack has about 8 volt cell voltage. Over time, after less than an hour, the voltage goes down by 2.6 volts. So it looks like that one of the cells is not working properly anymore, because we are losing the voltage of one cell in this overall series of 3 cells in a stack. And what we observe is that at 60 degrees C, this happens, that melting takes place of this PEO-based electrolyte. So basically what we have an ionic short circuit as shown here, and the polymer is moving to the next cell. And you can really simply avoid this by using a larger current collector area, which does not allow the polymer to move to the other cell. And even if it does not melt, a polymer is always soft, and at higher temperatures and with time, this always has to be regarded that there is a possibility that the polymer is creeping to the neighboring cell and then leads to an ionic short circuit. Then we have another problem which we observed, and this is that the copper current collector does not work, which is really a pity, because copper has such a high conductivity that even at very thin copper foils give us a very nice fast charge capability. That's the reason why many of us are using stainless steel, because stainless steel is something which does not corrode in the environment that sulfide-based electrolyte is providing. So stainless steel instead of copper then gives us also for this cell, for this 3 cell stack, then let's say proper cycling. So what we learned from this, it's very simple experiments, is that when you are going from lithium-ion to lithium-metal batteries, and when you are going from liquid electrolyte to solid electrolyte, don't take anything for granted. Everything has to be looked at carefully, and I think all these simple things make it, let's say, easier to develop not only the electrochemistry and chemistry for a solid-state battery, but also the processing for a solid-state chemistry. This is actually then the final slide. I want to make you aware that at the end, all these approaches that I have shown for lithium-ion, lithium-metal batteries somehow need to be merged. We need a good material, we need a good processing, we need a good formulation. Then future cells will be developed, and novel techniques and tools are required to find these future cells. And apart from performance and costs, very important also is that two more factors have to be considered key for future battery technology. So the battery of the future does not only have to show you good performance and low costs, it has to be sustainable both in the material and the processing side, and it has to give you an holistic safety. It should not get fire, it should not explode, and it should not be toxic. And this actually is only able with technique and tools to enable advanced lithium-ion and lithium-metal batteries. Some of them I have presented here, and I would like to thank you all for your attention. Thank you for being with you.
Thank you, Professor. I'm so glad I stayed up until so late so I can hear this talk today. Thank you. So there's a question for you.
I hope you have a good coffee, Shirley. I hope you have a good coffee.
I had my third cup for tonight.
Very good.
There's a philosophical question for you. Which do you believe should be considered as more critical? Technology with higher performance and low cost, or technology with high sustainability and better safety?
Yeah.
Let's say we cannot achieve both. Which would be more critical for you?
I think at the end, depends on the application. So if the application is not demanding too much performance from the cell, because you know the performance depends on how you use it. For example, delta SOC, how much SOC you are using, then the sustainable and green chemistry is something which will have always an advantage. In EU, for example, you know, it is the use of lead in consumer goods is banned. So nobody is allowed to use lead in consumer goods. A car is a consumer good, and a lead acid battery always contains lead. But depending on the application, if there is no better solution available, it's not a question of cost, it's really of the technology solution. So then the use of lead is still allowed. So I think the same we will also experience with lithium-ion, lithium-metal batteries. We will have some where we make compromises in performance for the sake of sustainability and safety. Yeah, but at the end, I think we will also see there a variety of chemistries, unless we can close the gap between sustainability, safety, and performance and cost on the other side.
Thank you, Professor Winter. I think the answer is full of wisdom. It takes us some time to digest, but I tend to agree with you. The application is very important when we make these compromises. Thank you very much for sharing your ideas and the wisdoms with us today. I think we will move to the next talk. I hope I have more opportunity to have discussions with you on this topic in the future. Thank you, Martin.
Thank you, Professor Ming.